Welcome friends, Igor is here, and in this video we will discuss matrix diagonalization. In this lesson we will define the notion of diagonalizable matrices, we will derive a criterion for a matrix to be diagonalizable, we will learn how to diagonalize a matrix if possible, and we will discover one cool application of the diagonalization. Let's get started. First, let's formalize the definition of a diagonal matrix. A square matrix is diagonal if each entry in position ij is equal to 0 as long as I is not equal to j. There are several advantages to having a matrix in a diagonal form. First of all, you see right away what the eigenvalues are because they are the entries on the diagonal of the matrix. Also, it is easy to perform other types of computations with diagonal matrices. For example, to raise a diagonal matrix to a power, you simply raise all entries on a diagonal to this power. We are going to say that a square matrix is diagonalizable if it is similar to a diagonal matrix. This 3x3 matrix B is diagonalizable because it is similar to this diagonal matrix A via the non-singular matrix R. We have worked out this example in the previous video. But in that example, the matrix was given to you, and the question is, how did I know to use this particular matrix to obtain the diagonal matrix A? We will answer this question in this video. First, we are going to establish a criterion for a square matrix A to be diagonalizable. A square matrix A of size n is diagonalizable if and only if there exists a set of n linearly independent eigenvectors of the matrix A. The eigenvectors of a square matrix of size n are column vectors of size n, and they live inside the vector space Cn, which has dimension n. Therefore, a linearly independent set of size n in this vector space is automatically a basis. We have proved this in one of the previous videos. This was called the Goldilocks theorem. Therefore, the criterion for a matrix to be diagonalizable can also be rephrased in terms of the basis. A square matrix is diagonalizable if and only if there exists a basis of the vector space of column vectors which consists of eigenvectors of this matrix. This theorem is an if and only if statement, so we are going to establish two implications. First, we are going to assume that there exists a set of n linearly independent eigenvectors of the matrix A, and we will prove that then the matrix is diagonalizable. So let S, which is a set of vectors x1, x2 through xn, be a set of linearly independent eigenvectors of the matrix A, and let's say that these eigenvectors correspond to eigenvalues lambda 1, lambda 2, up to lambda n. We are going to construct two matrices. The matrix R is constructed using these eigenvectors as columns. The matrix D is constructed by taking scalar multiples of the standard unit vectors by the eigenvalues of the matrix A. Let's observe that R is a non-singular matrix. This is because its columns form a linearly independent set. I will now show that the matrix A is similar to the matrix D, and I will use the non-singular matrix R for this. First, we are going to look at the matrix product A times R. We represent the matrix R using its columns, and then we recall the definition of the matrix product using the matrix vector product. The columns of the product matrix are the matrix vector product of the matrix A with the columns of the matrix R. However, the vectors x1, x2, and so on are the eigenvectors of the matrix A, which correspond to eigenvalues lambda 1, lambda 2, and so on. On the other hand, we are going to compute the matrix product R times D. Please check that this matrix product results in the matrix whose columns are the scalar multiples of the eigenvectors by the corresponding eigenvalues. But now, this computation shows that A times R is equal to R times D. The matrix R is non-singular, therefore it is invertible. If you multiply both sides of this equation on the left by R inverse, you will get an equality R inverse AR is equal to D. Therefore, the matrices A and D are similar, and this means that the matrix A is diagonalizable. This is exactly what we are trying to prove. But this part of the proof does more than simply show our claim. It is in fact a constructive proof. We have explicitly constructed a non-singular matrix that performs the similarity transformation. This matrix uses eigenvectors of the matrix A as columns, and we know which diagonal matrix we will get as a result. The entries on the diagonal of this matrix are simply the eigenvalues of the matrix A. Moreover, the order of these eigenvalues is equal to the order of their corresponding eigenvectors in the matrix R. Now, let's prove the other implication. We are going to assume that the matrix A is diagonalizable, and we will need to prove that it is possible to find a linearly independent set of n eigenvectors of this matrix. If the matrix A is diagonalizable, then there exists a non-singular matrix, let's call it T, such that T inverse AT is a diagonal matrix. Let's call this diagonal matrix E. Let's label the columns of the matrix T by y1, y2 up to yn, and the entries on the diagonal of the matrix E are d1, d2 up to dn. We are going to follow a similar computational approach as in the proof of the other implication. Given that T inverse AT is equal to E, this is equivalent to saying that A times T is equal to T times E. We can get to this equality if we multiply both sides of the previous equation on the left by the matrix T. Let's compute the product A times T. We represent the matrix T using its columns. Then we use the definition of the matrix multiplication in terms of the matrix vector product. And for the product T times E, we notice that it is easy to multiply by the diagonal matrix. So we know that A times T is equal to T times E. Therefore, the orange matrices are equal to each other. In particular, they have identical columns. Do you see what these equalities say? Do you agree that they say that the vectors y1, y2, and so on are the eigenvectors of the matrix A, and they correspond to the eigenvalues d1, d2, up to dn? Actually, not quite. Do you see what we're still missing? To qualify for an eigenvector, the vector must be a non-zero vector. So we need to check that all the vectors y1, y2, and so on are non-zero vectors. But they are columns of a non-singular matrix. Therefore, they cannot be zero vectors. This verifies that the vectors y1, y2, and so on are the non-zero vectors, and therefore they are eigenvectors of the matrix A. Moreover, they are linearly independent because they are the columns of a non-singular matrix T. And so, we have proved that if the matrix A is diagonalizable, then it is possible to find a set of n linearly independent eigenvectors of the matrix A. The proof of this theorem gives us a recipe how to diagonalize a matrix if possible. Step number 1 is to find n linearly independent eigenvectors of this matrix and the corresponding eigenvalues. Then we construct a non-singular matrix S by using these eigenvectors as columns in the matrix. Finally, the proof of the theorem tells us that the matrix product S inverse AS must be equal to the diagonal matrix, where the eigenvalues are the entries on the diagonal. Let's apply this procedure to a sample matrix. In one of the previous videos, we have considered this 3x3 matrix F. We have found two eigenvalues, 3 and -1, and we found the corresponding eigenspaces. This matrix F is diagonalizable as long as we can find 3 linearly independent eigenvectors. 2 linearly independent eigenvectors come from the basis of the eigenspace corresponding to the eigenvalue -1. These two vectors are linearly independent because they are a basis. And also we do have a third eigenvector, which is a basis of the eigenspace corresponding to the eigenvalue 3. But what happens if we put all these three vectors together? Will we still have a linearly independent set? Yes, because in one of the previous videos we have proved that if you mix vectors that correspond to distinct eigenvalues, they are automatically linearly independent. So let's define a 3 by 3 matrix S by using the vectors from the basis of all eigenspaces. We know that these eigenvectors are linearly independent and therefore S is a non-singular matrix. Also, by the proof of the previous theorem, we know that S inverse Fs is a diagonal matrix where the first entry on the diagonal is the eigenvalue that corresponds to the first column in the matrix S. The second value on the diagonal is the eigenvalue that corresponds to the second column of the matrix S, which is one of the eigenvectors. And the third value on the diagonal is the eigenvalue that corresponds to the third column of the matrix S. We have found three linearly independent eigenvectors of the matrix F. Therefore, the matrix F is diagonalizable, and we have found the corresponding diagonal matrix. In this example, we were able to find sufficiently many linearly independent eigenvectors by putting together vectors from the basis of the eigenspaces. But what happens if taking vectors from the basis of the eigenspaces is not enough? Well, in fact, in this case, the matrix is not diagonalizable. The criterion for a matrix to be diagonalizable is simple. A square matrix is diagonalizable if and only if the geometric multiplicity of each eigenvalue is equal to the algebraic multiplicity of each eigenvalue. Let me put this result in perspective. In one of the previous videos, we showed that the geometric multiplicity of each eigenvalue does not exceed the algebraic multiplicity of each eigenvalue. Also, we know that algebraic multiplicities of all eigenvalues add up to n, the size of the matrix. Therefore, the only way for us to find sufficiently many vectors in the basis of the eigenspaces is for the sizes of all these bases to add up to n as well. But the size of the basis of each eigenspace is the dimension of the eigenspace, and the dimension of the eigenspace is exactly the geometric multiplicity of the corresponding eigenvalue. If at least one geometric multiplicity is less than the algebraic multiplicity, then adding up all geometric multiplicities will result in something that is strictly less than n. And then you will not be able to find n linearly independent eigenvectors of the matrix A, which means the matrix A will not be diagonalizable. Here is an example of this idea. We have this 4 by 4 matrix B. We can compute its characteristic polynomial, and let's look at the eigenvalue 2. It turns out that the eigenspace corresponding to this eigenvalue has dimension 1. So the geometric multiplicity of the eigenvalue 2 is equal to 1, but its algebraic multiplicity is equal to 3. Because at least one geometric multiplicity is smaller than the algebraic multiplicity, it means that the matrix B is not diagonalizable. So, when can we guarantee that all geometric multiplicities are equal to the corresponding algebraic multiplicities? Well, this is simple. If all algebraic multiplicities are equal to 1, then the geometric multiplicities will also have to be equal to 1, and they're all equal to each other. When will this happen? Well, this will happen when a square matrix of size n has exactly n distinct eigenvalues. In this case, the matrix is automatically diagonalizable. Let's suppose that this square matrix A of size n has n distinct eigenvalues. Then we take one eigenvector for each of the eigenvalues. We have n eigenvectors of the matrix, and they are automatically linearly independent because they correspond to distinct eigenvalues. This means the matrix A is diagonalizable because we have found a set of n linearly independent eigenvectors of the matrix A. There are many applications of the notion of diagonalization because performing computations with diagonal matrices is much simpler than performing computations on generic matrices. Let me illustrate this idea by looking at one cool application. Here's a problem. We have this 2 by 2 matrix A, and we need to find the limit as k goes to infinity of the matrix A raised to the power k. The challenge is that you cannot solve this problem directly, because there is no way to find a general form for expressing the entries of the matrix A to the k as functions of k. Well, let's observe that this matrix A is diagonalizable. This might be a good exercise for you to check your diagonalization skills. But notice that raising a diagonal matrix to the power k is the same as raising the matrix S inverse AS to this power k, which simplifies to S inverse A to the k S. But now, if you multiply both sides of this equation by S on the left and S inverse on the right, this says that A to the power k is equal to S times D to the power k times S inverse. And the idea is that it is easy to raise diagonal matrix to integral powers. For this, we just need to raise every diagonal entry of this matrix to the corresponding power. But now, we can compute this product. Please check that this product is given by this formula. But now, when you take the limit as k goes to infinity, all those fractions raised to the power k tend to 0. Therefore, what's left is this simple 2 by 2 matrix. If you found this video useful, please give it a like to help others discover this content, and subscribe to this channel to see more of these videos. In the next video in this series, we will introduce linear transformations. I will see you later.